So let's go back and continue examining forces. And let's talk about what we already know. Here's my brick sitting on this countertop. And we know that this brick exerts a force. Now, a brick can't physically push or pull like a person can with their muscles, and has no engine to provide a force to push it or pull it. The only force provided by this brick is its weight, which is a function of gravity. Basically, the Earth's gravity pulls this brick down, pulls down on its mass, and the brick has a weight, and the weight is a force that acts down towards the Earth. You should also realize the more massive the object is, the stronger the force of gravity, because the greater the weight. More mass equals more weight. So we've got a force provided by this brick, which is its weight going down. The brick's motion is not changing. Well, that means this brick is in equilibrium, which means all of the forces acting on it must be equal. So if the brick's motion isn't changing, there is an equal and opposite force acting against the brick's weight, which is going down. That force is being provided by this table. The brick isn't moving that way, even though there is a force pulling it that way, because the table pushes back. The force that is provided by a surface of contact is called the normal force, and it always acts perpendicular to the surface of contact. Well, this table is flat. Weight is pushing that way. The normal force is pushing this way. So if we want to describe what we got right here, we've got this situation right here. We've got the weight of the brick pushing down or pulling down, and we've got the normal force provided by the table going back up. So right now, everything's in equilibrium. Motion is not changing. I'll take my handy dandy little spring scale, which measures force, and I will hook it to this brick. And I go to pull on it, and I am pulling with 4 newtons of force. Well, now this changes my free body diagram. I'm exerting a force this way. So on my free body diagram, I've got a force going that direction. Capital F for force. We'll call it the Weigand force. Usually forces are forces. They are denoted differently by a subscript. So in this case, we've got a normal force. Weight is always a W because weight is weight. It's a very special force. In this case, we got a pull provided by me. So we got a Weigand force. Now, I was providing a force of 4 newtons this way. Look at my free body diagram. Now I don't have it expressed as equilibrium. It looks like I've got more force going this direction, and there isn't a force going that way. Well, an unbalanced force will cause a change in motion. And as it looks, as I have it drawn here, it seems like the brick should move this way because there is a force going this direction and there is no force going that direction. And that mystery force is the one we're going to talk about today. Most of you realize why this brick is not moving, because there is friction between the brick and the tabletop. Friction is a force. It is a push or a pull. And in this case, we can see the friction must be working against me. I can pull with a force of 4 newtons and the brick doesn't move. That means the frictional force going this way against me must be at least 4 newtons. Now, if I pull with a force of 9 newtons, well, now the brick starts to move this direction. So that means the force provided by friction was something more than 4, and it was something less than 9. Because once I got to 9 newtons, the brick did change its motion and started to move that way. So let's define that frictional force. Let's put it in words. Frictional force is the force that exists between 2 surfaces in contact. You know that to be true. If the brick weren't touching the tabletop, there would be no friction between them. 2 surfaces have to be in contact in order for there to be friction between them. One important aspect of frictional force is that it always works opposite the motion or opposite the applied force. Friction never works with you. It always works against you. And if you think about pushing something across the floor, if I pull on it this way, the friction is working against me that direction. Now, if I pull the brick this way, well, in this case, the friction is working that direction. So the frictional force always works opposite the motion or opposite whatever force you apply. All right, so we got this idea of the frictional force, but what determines the frictional force? What makes its value? What makes friction more or less? Well, you should have a basic understanding of friction, and you know that the surfaces in contact really determine the amount of friction. You know there's a lot less friction on ice than there is on sandpaper. So the two surfaces in contact directly determines the amount of friction or the amount of frictional force you're going to have. But there's another thing that makes a big difference, and that is the mass or the force we have here. If I pulled on this, I said I got it to move once it got to about 5 newtons. Same surface. It's still brick on a countertop. So the surfaces are the same. That's not going to change the frictional force. But I now notice that if I pull on this, it takes about 15 newtons to overcome the friction and get this thing moving. So the weight seems to have an impact. But in reality, it's not necessarily the weight directly. It's this force that is pushing back against me. That normal force greatly determines the amount of friction or the amount of frictional force that we have to overcome. And you know this, that pulling these 3 bricks is a lot harder to slide than 1 brick. You also know that if I was sliding this across the tile floor, it would be easier than if I were dragging it across carpet. And if you've ever had to push a piece of furniture from the carpet onto a wood floor or a tile floor, you know there's a big difference in the amount of force it takes. So to answer our question here, the amount of frictional force depends upon the surfaces in contact and the normal force, which is directly related to how much the object weighs, because the weight is opposite the normal force. So here's how we determine the amount of frictional force. The frictional force, or the force of friction, and sometimes you'll see this denoted with a little f down there. Matter of fact, frictional force is determined by or is equal to, this is the Greek letter mu. Looks like a letter U with kind of a long tail on the front end. This here is called the coefficient of friction. It is a number that tells you something about the friction between surfaces in contact. This is a standard. This is a constant. This is something that you look up. There's a value for this for glass, for concrete, for carpet, and it has to do with the two surfaces. So this is a number we look up for the amount of friction between, a glass container sliding on a tile floor, or a wooden box sliding across carpet, or a rubber container sliding across a wooden surface. This is a constant value that we just have to look up. In the course of us doing our physics problems, this will be given to you. This here we know is the normal force, which is directly tied to the weight. This is the force that is provided by the surface that the object is in contact with. In most cases, this is going to be equal to the weight, so long as the surface is horizontal. The weight pushes down, the normal force pushes back up. Now, as it turns out, there's one other thing about the frictional force that we need to consider. And you've all experienced this before. Once you think about moving this brick or moving any heavy object that you have to slide across the surface. If I push on this and I have to push with a certain amount of force, and once I get it moving, it actually takes less force to keep it moving. If you've ever had to slide a couch across the floor, you know, kind of once you get that couch moving, it'll stay moving a lot easier than if you stop and then have to start over again. That's that inertia aspect that you have to overcome. So once you get something moving, it wants to stay moving. And therefore, the frictional force isn't as hard to overcome. And we can do this mathematically here with the spring scale. I get this up to about 5 newtons. But once it starts to move, the number on the spring scale only registers 4. So it takes 5 newtons of force to get this thing moving, but it only takes 4 newtons to keep it moving. And that's because friction works differently if something is sitting still versus if it is moving. And there are terms for that. It's called static friction. Static friction is the frictional force when something is not moving. Kinetic friction is the frictional force when something is moving. So there's different values, which means coming back to this right here. When we have the coefficient of friction, this is dependent upon if it is moving or if it is sitting still. You have a coefficient of static friction. In other words, when the two things are sitting still, what's the force between them? But you have a coefficient of kinetic friction, which tells you something about how much frictional force there is between objects once it gets moving. So 2 types of friction: static friction, sitting still; kinetic friction, moving friction. Now let's consider this situation here. Look at what's different. Now we've got wood in brick instead of the countertop in brick. Well, these are now 2 different surfaces, which means there's going to be different friction between them. If I pull on this, man, I can get this up to like 8, 9 newtons before it starts to move. That means the coefficient of friction between the brick and the wood must be higher than the coefficient between the brick and the countertop, which this kind of makes sense because the countertop's pretty dense and it's pretty smooth. So things will slide easier on this. Wood is fairly soft. So the brick kind of digs into the wood, which makes more frictional force that I have to overcome to get it to move. So the frictional force is different between the different surfaces, but I will notice this is the same. I get to about 8 and it starts to move, and then all of a sudden it only takes about 6 to keep it moving. So remember, the kinetic or the moving friction is always less than that static friction. So now let's start examining the real nitty-gritty here. And that's the fact that the world isn't perfectly flat. We have hills, we have inclines, and that's going to change our friction. And I can point this out to you very easily. If I hold this brick on this ramp, I want you to consider the free body diagram here and what's happening. The brick has a weight that goes straight down. The board or the ramp provides a normal force against the weight, kind of. Remember, the normal force acts perpendicular to the contact. So when the brick was like this, my normal force worked directly against the weight. When my ramp is like this, my weight still is pointing straight down, but my normal force is actually like this because it's perpendicular to the ramp. So that's a case where now my normal force is not as big as it once was. Here, my normal force is equal to all the weight of the brick. Here, the normal force is actually less because the weight is still pushing straight down or pulling straight down, but my normal force is now at an angle. What else is acting on this brick? Is there a force that is pulling this brick down the ramp? You should realize there is. That gravity wants to pull things down the hill, but the brick's not moving down the hill. We know there's a force pulling that way. What's keeping the brick on the ramp? That's friction. So there's a component of the brick's weight caused by gravity that is pulling this way, and there is friction that keeps it from sliding down the ramp. Now, same situation here. Now there's a lot more pull from gravity down this ramp, but it's still not a big enough pull to overcome the friction. We still have weight pulling straight down, but now my normal force is even less because my angle is steeper. If I eventually get to a point, you know what's going to happen. If this ramp gets steep enough, the motion of the brick changes. Once the ramp got steep enough, the pull of gravity down the ramp was enough to overcome the friction that was keeping the brick stationary. And you saw what happened. The motion of the brick changed. It slid down the ramp. Well, remember that the frictional force is determined by two things. That coefficient of friction, which is whatever two surfaces are in contact. I didn't change. It was brick and wood the whole time. My normal force was getting less as I raised the ramp. So as this got less, that means the frictional force got less. And eventually the frictional force was so little that gravity was able to overcome it and the brick started to move. Now, we need to draw a free body diagram of this to be able to describe the forces that are in play here. Okay, so on a flat surface, here's what we've got. Got a brick in contact with the surface. Nobody's pushing or pulling on it, not introducing friction here. We've got the weight pulling down and the normal force pushing up. Now let's look at what's different here. Here's my brick on an inclined plane. I still have a weight of the brick pulling down. That doesn't change. It still has a mass, and it's still being pulled towards the center of gravity down here towards the earth. The weight always acts directly down. But remember that the normal force is perpendicular to contact. So because the ramp now, the surface is now at an angle, the normal force is also now at an angle. Imagine this. If I brought this angle down, 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 down until it got flat, the normal force eventually ends up being perpendicular, being the same as the weight. If this angle gets bigger and bigger and bigger, this vector here, this normal force ends up being less and less and less. Think about a vertical board. It doesn't push against the brick at all, and the brick would end up falling straight down. So we have this angle here measured. Let's call it theta. And for now, it's just going to be a generic angle. We can put in a number, and we will when we get to that point. Now, I can go through the geometry of this, and I know how much you guys love geometry. And if you want me to prove this to you, I would be more than happy to go through this. But you can kind of see that there's some right triangle stuff in here going on, that we can take this angle and, with parallel lines and all kinds of, we can make some triangles, and then we can do that Sokotoa stuff, and we can figure out of this weight, what portion of it is going down the ramp and what portion of it is pushing away from the ramp equal to the normal force. And I'm just going to go ahead and give this to you, and you're going to copy this down. The force that gravity pulls down the ramp. Now, mg, we've seen mg. That's equal to the weight. It's mg sine of theta. It's the weight of the object, but it's only part of the weight of the object, because it's kind of like when we did two-dimensional motion, and we had something with a velocity at that, we know some of it was in X and some of it was in Y. Well, now when we have an angle, some of the weight is working one direction and some of the weight is working the opposite direction. And what happens, the force of the weight coming down the ramp is found by mg sine of theta, and the normal force, as you can probably guess, is mg cosine of theta. Now, we also have a force of friction. And the force of friction is that. It is whatever the two surfaces are times the normal force. And the normal force is some function of the object's weight. If this ramp were totally vertical, there wouldn't be a normal force and it would go straight down. There wouldn't be any friction because they wouldn't be in contact anymore. And the force pulling something down would be just equal to the weight. It'd be like there wasn't a ramp there. So this is a very important relationship. Like I said, I could go through the geometry of this, but what you need to recognize is have this and realize, okay, the force that pulls something down a ramp is its weight, mg is the weight, times the sine of whatever that angle is. The normal force now is mg cosine of theta, the weight times the cosine of whatever that angle is. Weight is still weight, it still works down. And that the frictional force is this right here. Now, as this angle gets bigger and the friction and the normal force gets smaller, means the friction gets smaller. And this is why a really steep ramp, things slide down easy because the friction ends up being really small. If this angle gets pretty short, pretty tiny, well, the normal force gets bigger, which makes the friction bigger. Things don't slide down a gradual ramp on their own very easily because the friction is just too big. Okay, so now I think you've got this diagram here and the relationship with friction that you need in order to be able to solve the second set of problems, which Ms. Campbell will then go over with you tomorrow.